Okay. Okay, bear with me. Coffee break soon. Okay, and another English presentation. I'm so sorry about that. So I'm here to present my work on semantically meaningful metrics for Norwegian ASR system. So we've been talking about ASRs, and the most widely used metric to evaluate speech recognition models is the word error rate. So the word error rate simply is the number of word errors divided by the total number of words in the sentence. And all the errors in the metric is weighed equally. So just a simple example. For example, someone says, this is a cat. One model transcribes it as this is a bat, and another transcribes it as it is a cat. Naturally, if you read this, you would say, okay, the second model transcribes it better. But just looking at the word error rate, you have no way of judging that one model is actually better than the other. So that is the problem with word error rate. So as I've said, not all errors are equal. So it doesn't really encompass the inequality in these errors. And what we want and what motivated us is to explore a more robust and semantically meaningful metric compared to word error rate. And especially useful for Norwegian, as we have been speaking about this afternoon. These are the characteristics of the language. I'm particularly fascinated with the compound words here, for example, which just means mother. It's a mom, the chief administrator of a family with small children. But you would say it like this also, which is fascinating to me. So what is our proposed solution? We want to use semantic information. So recently developed language models have been able to capture semantic information, and we want to utilize this information. So we can use these language models to represent text in the form of embedding vectors, which are basically just numerical representations. And the idea is that these numerical representations, if there are, for example, words like apple, orange, and bread, would be closed in the vector space as opposed to like the cars, the vehicles. So when I started my PhD work, there was already an existing semantic-based metric called semantic distance, shown here from Kim et al. In their metric, they extract embedding vectors for the reference and the hypothesis text. They take the average and then compute the distance between the two. They do the averaging because in reality, you would have different lengths of embedding vectors. However, we found that averaging it, you would actually lose some information there. You would blur out any differences or like intricacies in the embedding vector. So what we propose is to actually align these embedding vectors. In our method, we want to find the optimal alignment between the embedding vector for the reference and the hypothesis, and then find the total distance. So we use dynamic time warping to find the optimal alignment. So to extract the embedding vectors, we use a transformer-based language model called Norbert. I'm sure you're familiar because it's an old model. And we've applied it to several transcriptions of various speech data, so NBTALE, Rungast, and Stortingen. As I've said, it does a word-to-word, or I guess in this case, subword, comparison of the embedding vector and finds the optimal alignment between the two. So in our experiments, what we found is that, as I've said, the averaging in SEMDIS, we feel like it blurs out the information. So if you have longer utterances, the metric would give you naturally lower values. So if you have any difference there, it would just be averaged out in the length of the utterance. But in our metric, it's actually robust to the utterance length. So it's just a line graph here. You would see like with longer utterance length, ASD or aligned semantic distance doesn't really result to lower values. And then we saw that it also provides a more meaningful like measure. For example, if you have wrong words such as like verbs or proper nouns like company names, the metric gives you a higher penalty as opposed to when you just have the preposition or a pronoun mistakenly in the transcription. And lastly, it's useful for the region. So we did some examples, or like we tried to replace Bokmal words with its New York equivalent. it didn't really give you a high penalty. So as opposed to word error rate would give that automatically, okay, that's wrong. That's completely wrong already. In this semantic distance-based metric such as ours, it doesn't really give you a high penalty. Maybe some little mistake only, you know? So we've been like talking about the advantageous properties of the metric. However, how can we say that it's actually useful for the end users, for us? So we went further and we investigated or we assessed the metric on two things: perception and its performance on downstream tasks. So first, it's perceptual assessment. So we performed a survey asking participants to rate transcriptions from 1 to 5, 1 being the lowest and 5 being the highest score. So what we saw is that word error rate and aligned semantic distance will be more correlated to human perception. So we took that a step further and say, is it feasible for us to predict how humans perceive the quality of ASR models? So how they perceive how good it actually is. So we just did a simple classifier here where the model predicts, for example, I give you a transcription. The model should predict what would be the perception of the human evaluation or the score would be, based on the input, like word error rate or ASD score. And ASD score was better at being a feature for this kind of prediction. We also did some linear regression models which show that it also has lower errors, lower MSE, and a higher coefficient of determination. And the next part is the task-oriented part. So we don't just normally use ASR as it is, like just transcribe. Normally, it also has a downstream task, for example, named entity recognition or sentiment classification. So what we did here is that we took our baseline transcription and simulated errors. So what we want to prove is that you have equal word error rates, but you could have a varying score for aligned semantic distance. It could be lower or higher. So what this demonstrates is that for lower aligned semantic distance score, you actually have higher F1 scores on both the downstream task NER or sentiment classification, and vice versa. So while word error rate is unable to give you a meaningful indication of how the model would eventually perform on these two tasks, our metric is able to give you a more, you can be more sure. Okay, I have a lower ASD score for this model. This will perform better on my downstream tasks, especially these two, which are mainly, like, they really depend on the meaning. Named entity recognition is in the name itself, and sentiment classification. Okay, so this is my last slide. We can go for coffee soon. So my current work. So it naturally, like, to me, it was natural that the progression of my work would go into, say, we have this semantic-based metric. Why don't we use it to optimize models? For years and years, it was all about making the word error rate low. We have to go as low as possible. But it's not all about word error rate. We can also go, like, in this direction where we go with the lowest semantic distance. It should be as close as possible to the mean. As have been mentioned before, it's not really transcriptions or like reference transcriptions are really based on what the speaker wants. It's based on like Ninorsk or Bokmal. But if we can use something that's more meaningful than word error, then we can optimize for the meaning as opposed to not like just the spelling or just the word itself. So I've been working with the WAV2VEC2 model because simply it's what I've started before. I know there's Whisper now, but I've been working with the WAV2VEC model to use ASD as part of the optimization criteria for it. And another part of my work is I want to apply it to other languages, of course. So, yeah. That's it for me. Thank you so much.